to the talk of Francesca Maggioni from Bergamo, Velocity, Energy and Helicity of Vortex Knots and Unknots. Francesca.
Thank you very much. Does it work now? Yes. Thanks, Renzo, for the introduction. I would like to thank also the organizer for the opportunity to give this presentation. This work has been done in collaboration with the Sultan alumni, Professor Carlo Barenghi and Professor Renzo Ricca. And after the existence of solution of vortex knots, now we will see some dynamics of vortex knots in the context of ideal fluids. So I will start by giving you the general context in which we're supposed to work. We consider the case of an ideal fluids in which we have the equation of the motion governed by a velocity vector field u, described by that is a smooth function of a vector position x and the time t, and which has to satisfy all of this relation, that is its curl gives us the vorticity, its divergence less, and the velocity is equal to 0 at the boundary of the domain. In ideal conditions, so in absence of viscosity, the fluid motion is governed by the Euler equation, and in ideal fluids we have several topological quantities that are conserved during the evolution, and also some physical quantities such as vortex circulation, momenta, kinetic energy, where the V represents the volume of integration, U again the velocity, kinetic helicity, and topological quantities such as the knot type, linking number, and the crossing number. So all these quantities will be considered conserved during our evolution. The purpose of our work was to compare different geometric and topological structures in terms of their dynamics in the case of ideal fluids. So for this reason I will briefly recall the general setting of the notation that we use to describe a space curve that will represent our knotted curve in space. It will be denoted by a parametric equation x, smooth function of the arc length along the curve, and t, which represents a kinematic parameter. So our curve will be represented, the geometry of this curve will be represented by the Frene frame, described by a tangent, normal, and binormal vector to each point along the curve. And we will identify our vortex filament with the axis, with the filament axis of constant circulation gamma. In ideal fluids, the vortex line move according to the Biot-Savart law, where the vorticity now is retained inside the vortex circulation, and exact analytical results about solution according to the Biot-Savart law are very difficult to obtain. So several asymptotic techniques have been developed in literature, and the crudest approximation of the Biot-Savart law has been done by Darius in 1905. Oh, sorry. And this is given by the so-called localized induction approximation, which tell us that the velocity goes according to the binormal vector, and with a velocity which is directly proportional to the curvature of our curve. So this localized induction approximation is obtained by applying an asymptotic theory, and so assuming that the vorticity is constant during the evolution, the thin tube approximation, so we suppose that the ratio between the biggest radius of the vortex with respect to the small radius is much greater than 1, and there is no self-intersection. So in this, by means of this free assumption, it has been proven that the velocity is proportional to the curvature in the binormal direction. And under the localized induction approximation, several quantities are conserved and can be expressed in terms of geometric quantities For instance, the energy is proportional to the square of the curvature, the helicity to the square of the curvature multiplied by the torsion, the writing number is again proportional to the energy, and the total twist number is proportional to the total torsion, because the intrinsic twist of the filament is equal to 0. So we will test several geometric and topological structure under Biot-Savart law and localized induction approximation, which have the shape of torus knots. So for this reason, I briefly recall what we mean for torus knots. We mean a curve that cut a meridian of a torus p time and a longitude at q time. So a torus knot will be identified by two numbers, a number p and a number q, and the ratio between these two numbers will be given us the winding number. So we will denote by now on, by W, the ratio between the number of longitudinal wraps with respect to the number of meridional wraps. For instance, in this figure we can see two different representations of a trefoil knot, which are topologically equivalent, but they have different geometries. The first one is obtained by three turns in the longitudinal direction and just 2 turns in the meridional direction. On the other hand, this one has 2 turns in the longitudinal and 3 in the meridian direction.
Could
Yes.
you please just explain your color?
No,
code?
no, here just no the color,
It's
just
got to do with direction.
no, it's just from a representative point of view. No,
And nothing more.
no, it doesn't.
No
It doesn't.
information content, just beautifully things.
Yes, just just
That's
representation.
frustrating.
Okay, so these are two topological equivalent representation of the same trefoil knot. Yes, and it was no, the color doesn't match. It's just a representation. So in the case we have that the number of longitudinal or meridional wraps are equal to 1, then we have that the curve is not knotted, and so we call it a unknot. And in this case, we can have a representation like this. For instance, here we have a number in the longitudinal direction, a number m of coil in the longitudinal direction, and just 1 in the meridional direction. On the other hand, we have just 1 coil in the longitudinal direction and m coil in meridional direction. Again, these one are topological equivalent, and they are again topological equivalent also to the circle, to the standard circle. So this will be the structure that we will test in our numerical investigation under Biot-Savart law and the localized induction approximation. Why to test this kind of structure? Because analytical solutions were found by Kida in 1981 with the shape of torus knots. In fact, Kida found that in the case of an ideal fluids, then there exists a class of steady solution in the shape of torus knots in terms of incomplete elliptic integrals. Analytical results was then developed by Rick in 1993, which obtained a closed form, an analytical closed form based on linear perturbation of the circular solution of the nonlinear Schrödinger equation. So by linear perturbation of the circular solution here expressed in cylindrical polar coordinate, he found a solution which has the shape of a torus knot. And the unique analytical results about the stability of this class of torus knots is this one. So under localized induction approximation, the class of torus knots that it is stable under linear perturbation is the one in which the winding number is greater than 1. Okay, so this theorem gives us the main motivation to carry out the numerical investigation and to understand if also in the case of Biot-Savart law we have the same kind of result or not. And so now I will briefly show you the result of the numerical investigation. In the numerical setup we have discretized our space curve in a number of points, and this mesh density can be directly proportional to the curvature. So in the case of a higher curvature, the code will consider more points. And one important issue that we had to consider in the code was the desingularization of the Biot-Savart integral, because the velocity, it will be considered as the sum of two contributions, one local contribution and one non-local contribution. In the case of a local contribution, when the 2 points are the same, then the Biot-Savart law will be substituted by this localized induction approximation formula, where L plus and L minus represent the two nearest points to the point x in which we are going to make the computation of the evolution in time. So we have tested the convergence in time and in space, and now I will present you the general result that we get. First of all, let's analyze the different structure in terms of geometric quantities. In the case of unknots, we have that by setting the linking number equal to 0, the helicity is as well equal to 0 according to this relation, and then the contribution of the total twist number is just given by the opposite of the writing number. So let's consider the information about the writing number of different geometries and topologies that are plotted against the winding number. So on the x-axis, we will see an increasing value of the winding number, and on the y-axis, the writing number. We will see that the meridian wraps contribute modestly to the total writing number, but the dominant contribution comes from the longitudinal wraps. So in fact, we see that the longitudinal wraps give us a high contribution to this measure of contortion of the curve in space, and less contribution come in the case of meridional wraps.
Sorry, I was distracted.
Yes.
The difference between the red and the blue curve?
Yes, the red curve refers to torus knots, so the case in which the topology is not equivalent to a standard circle. The blue one represents torus unknots, so the one that are topologically equivalent to the standard circle. So all the computation will be compared with the standard circle here represented. So in general, we can see that for the circle, the writing number is equal to 0, and we have high values for this class of torus knots and unknot, in which we have longitudinal wraps greater with respect to the meridian wraps, and the same for the second class. So this is just a geometric information. Now we will focus more about the dynamics of this class of torus knots and unknots. First of all, we will investigate about the translation velocity under Biot-Savart law. We can see that again the velocity is compared with respect to the vortex ring. The red lines refer again to torus knots, and the blue one refer to torus unknots. And we can see that the velocity decreases with an increasing winding number, and the fastest torus knots are this one, that is the one in which there is a very high number of longitudinal wraps with respect to the one with a high number of meridian wraps. And interestingly, for a high value of the winding number, the torus knots tend to reverse their velocity, as has been proven by another paper by Professor Carlo Barenghi. So, interestingly, we can also compare the rule of the topology in this investigation. Again, in this graphic, we can see different structure of torus knots and unknots, which are compared in terms of the topology. So it means that on the x-axis, now we represent the number of P and Q, which represent our knots, so the number of meridian wraps with respect to the number of toroidal wraps. And we compare the velocity of a knotted configuration with respect to the corresponding unknotted. For instance, this one corresponded to the knots 21, 2, and this one corresponded to the velocity of the node of unknot 21, 1. So it means that is topological equivalent to the circle. The same for smaller values of longitudinal or meridional wraps. We can see that in general the velocity of the knots is higher compared to the velocity of the corresponding unknots. In this case, and so on. In general, we can see that this class of knots, so the one in which we have a very high number of longitudinal wraps, has velocity that is all the time higher with respect to the one of the standard circle. And in the other case, so in the case we have a very high number of meridional wraps, again it happened that the velocity of the knot configuration is higher compared to the unknotted configuration. We have also compared this class of knots in terms of kinetic energy. Again, the red values represent to the knotted configuration. Now compare with respect to the localized induction approximation. So now the red one represents the knots and the blue one represents the corresponding value for the localized induction approximation. Here all the class of figures that are represented are knotted solution, and we can see that in general for a winding number less than 1, the localized induction approximation underestimates the actual energy according to the Biot-Savart law. On the other hand, for a winding number greater than 1, we have that the localized induction approximation provides higher values with respect to the actual value of the Biot-Savart law. And the main reason of this is because the localized induction approximation doesn't take into account about the rotation and the non-local terms, so it takes just into account about the translation velocity on the direction of the binormal. The same for the class of unknots. We can see again that the localized induction approximation has quite good values compared to the Biot-Savart energy computation in the case of the winding number is less than 1. On the other hand, we have that for a very high number of winding number, the localized induction approximation overestimates the actual values of the energy, of the kinetic energy. And the reason is again the same, because it doesn't take into account of the non-local terms. Finally, we have also considered the structural stability of different topologies and geometries. The graphics here reported are in the case of torus knots with a winding number less than 1 that were found by the theorem in 1993 to be localized in LIA unstable. So the aim of this test was to try to understand if under Biot-Savart law this class of knots are Lie stable. And we found that all this class of knots are Lie stable, are stable according to the localized induction approximation and according to the Biot-Savart law. In fact, they travel for a distance that is higher than with respect to their actual dimension, like the diameter. In general, here we can see that for an increasing topological complexity, the distance that is traveled is less compared to the one with much simpler topological complexity, but all these class of knots are stable. So, in conclusion, we have evaluated by this numerical investigation the effects of geometric and topological aspects on the dynamic of torus knots and unknots. And in general, we have found that for a winding number less than 1, the more complex the vortex structure is, that faster it moves. And on the other case, for a winding number greater than 1, we have that all the vortex structure has a velocity that is close to the velocity of a standard circle solution, and so this is almost independently from their total twist. So it means that the total twist is a second order importance element. And the localized induction approximation tend to underestimate the energy in the case of a winding number less than 1, and to overestimate the energy for a winding number greater than 1. And we have also proven by a numerical investigation that the stabilized effects of the Biot-Savart law is obtained also for the class of knots with a winding number less than 1 that are Lia unstable. And here some references. This is the first work in which the investigation started, and the last two in which these results has been reported. Thank you very much for your attention.
Questions, please. Yes.
Well, you should be able to calculate what is the, say, minimum energy but maximum propulsion efficiency. It's going to be like a combination of, say, 2 or 3 winds, but well, not a single one with the maximum, well, with the minimum energy. And it should be very interesting if you've seen Paul Linden's and Turner's maximum propulsion, say, experimental vortices, which you can calculate it, well, as you should. Dolphins actually do something like that. They have like a combination of a big kick and a little kick. So there is some optimum topological kick or swim, and it's not simple at all. Well, can you do it, or can you comment, or how would you find the combination of the twists and knots that give like an optimal kick, or call it like that?
In this investigation, we just use that class of torus knots that were obtained as a solution of a localized induction approximation by standard perturbation of a circle. So, but it would be interesting also
like say,
yes.
Maximum proportion, minimum energy, coherent vorticity, some.
Perfect occasion for me to say, come to my talk. I will answer your question.
For practical Olympic swimming applications, very interesting. I know.
Yes.
So all the shapes of the vortex tubes that you investigated were smooth.
Yeah, sorry?
All the shapes of the vortex tubes that were investigated were smooth. I'm wondering if you considered. I wonder if you considered as the initial condition vortex tubes that were topologically equivalent, yet had small scale wiggles. If this would change the integral properties that you were analyzing.
It should be interesting. So this, we just consider this class of vortex knots and knots as the initial condition, and
right.
then we let to evolve according to the Biot-Savart law and the localized induction.
But if you impose some small scale wiggles on,
yes.
on the shapes,
yes,
which would still leave you the same topological structure, if this would change anything as far as the long-term evolution is concerned, do you have any insight?
No, but we should discuss about that.
Other questions? If not, thank you, Francesca.